Hello again. Today I want to show you the complete derivation of the solution to the motion of a system consisting of a mass and a spring. And the solution, the objective is to find actually the displacement of the mass as a function of time. So what we're going to do is to start first of all coming up with the differential equation, and then we'll look at the solution. So using second law, if you draw the free body diagram of the mass, it is clear that if you move the mass to the right by x, the force of the spring would be k times x. Now since this is the direction of disturbance, if we pick that as our positive direction, right, and just say sum of the forces equal ma, it's clear that the force of the kx going to the left, so that's negative, and acceleration of course is x double dot. So the differential equation clearly becomes mx double dot plus kx equals 0. The second order homogeneous differential equations. So to put this in the convenient format so that then we can go ahead and solve it, is that we normalize this by dividing by mass, and then we're going to call k over m, the ratio of k over m, to be natural frequency squared. In other words, the natural frequency omega n is the square root of k over m. So this differential equation becomes x double dot plus omega n squared x equals 0. So what I want to show you now is the solution to this differential equation, which is the differential equation for a simple system with a mass and a spring. Okay, so what is the solution? Solution for something like this, in this format, that you have second derivative plus something times the function itself equals 0, has to be an exponential function. So we assume that the solution is of the form of some constant a e to some power, I call it lambda times t. So, and the way you go about finding a and lambda eventually is that by substituting the solution that you've assumed into the differential equation. So you need x double dot here. So first we find x dot, which becomes a lambda e to the lambda t, and then we need x double dot. Eventually we need x double dot. So that becomes a lambda squared e to the lambda t. So let's go ahead and substitute that. So instead of x double dot, if I put a lambda squared e to the lambda t plus omega n squared times x, but x is right here, is a e to the lambda t. Notice that we can factor a e to the lambda t, and then we are left with lambda squared plus omega n squared. So how could we have a product of two parentheses equal 0? Either this parenthesis has to be equal to 0, which is not a good idea because that would be meaning the solution is 0. That's called trivial solution. Or this parenthesis has to be equal to 0. That's the better choice, and that will give us the roots of our system. So notice that the roots are going to be complex conjugates. Lambda 1 and lambda 2 are plus and minus I omega n. So we notice our roots are complex. So let's go to the next page. And now because we have two roots, therefore the solution is going to be combination of the two roots. Some constant a1 e to the power lambda 1t plus another constant, we call it a2 e to the lambda 2t. I have to mention that actually A1 and A2 will be determined actually based on the initial conditions, and right now A1 and A2 are complex, and they always come as paired, so they're complex conjugates. Let's go ahead and put actually lambda 1 and lambda 2 and see what we have to do. So remember, lambda 1 was, we go with the positive I omega n times t plus a2 e to the minus I omega n times t. Okay? So now we don't want to deal with complex powers. So we go ahead and use Euler equation, which is a very useful equation, which says, okay, e to the power plus and minus I theta is equal to cosine theta plus minus I sine theta. Actually, I'm running out of room, so let me move this over here. So e to the power plus and minus I theta is equal to cosine theta plus and minus I sine theta. So our equation now becomes a1 cosine omega nt plus I sine omega nt. And similarly, with the negative exponent here, the a2 cosine omega nt minus I sine omega nt, parenthesis closed. Okay, let's simplify this a little bit. You can actually factor cosine omega nt and combine a1 and a2, right? And then do the same thing for sine omega nt. So we have an I, actually a1 minus a2 sine omega nt, right? And now I can tell you that actually a1 plus a2 becomes a real constant. I'm going to call it uppercase a1, and the I times a1 minus a2 becomes also a real constant. I'm going to call it a2. You could easily prove this actually by doing the following. Just pick two arbitrary complex conjugate roots. Remember we said a1 and a2 are complex conjugates. So for example, if a1 is say 3 plus I4 and a2 is 3 minus I4, look, if you add a1 to a2, just to show you quickly, these get cancelled and we get 6. 6 is what? That constant. Of course, this is just a arbitrary, constant that I picked. But I just wanted to show you that the a1 plus a2 is going to be a real constant. And similarly, if you do a1 minus a2 and multiply it by I, you get a constant that is real. Okay, to the next page. Now our solution has become a constant a1, which is now a real constant, cosine omega nt plus a2 sine omega nt. And then anytime you have combination of sine and cosine, you could eventually make it one constant, either sine or cosine, argument omega nt plus some phase angle. So the next step is to find a and phi. A and phi are determined based on the initial conditions. And the initial conditions are typically the initial position. So at t equals 0, this is at t equals 0. X equals x0, and the derivative must be the initial velocity. So without going through the detail now, because this would be really easy, if you just plug in x0 here in this equation here and set t equals 0, actually, no, I can actually write it down for you. x0 becomes a sine phi easily, and v0 becomes a omega n cosine phi, and then by just some manipulation of the equations, you can then get the two constants that you want. Phi actually becomes inverse tan of x0 omega n over v0, and then the amplitude a. So remember, a is called the amplitude and phi is called the phase angle, and a becomes square root of v0 squared plus x0 omega n, the whole thing is squared, divided by omega n. So we started with a simple mass spring system, and we went through 3 pages altogether, and we showed that the solution to this system is going to be of this form, a simple harmonic system. So basically we're going to have something like this, where the this is the x0 and the slope of this, actually the slope of the tangent line to this, was going to be V0. Alright, thanks for listening. I'll show you more examples of this with numbers. Thanks again.